Welcome. In this tutorial, we will have a look at the practical applications of eigenvalue decomposition and more so that of principal component analysis that it facilitates. Let's get started. I will load some libraries here and I'll set a random seed for reproducibility since we are dealing with random numbers. Now my idea here is to generate a synthetic data set which is basically comprising of two random variables, and these two random variables have linear correlation. So my first variable is RV1, which I have taken from normal distribution having mean 0 and variance 2, and I will sample 100 such numbers. And then once I've got these numbers, I will generate random variable 2, which is nothing but random variable 1 multiplied by 2. This is what is going to create a linear relationship between these two variables. And I'm going to add some noise into this, which is again a random noise from normal distribution having mean 0 and a much lesser variation in comparison to RV1, that is 1, and I will generate 100 such numbers. So, and in fact we can just plot them so that you can have a feel of what is happening. So this is for RV1, and let me just enable my plot. So what you're seeing is a random variable, this is RV1, and I can also generate RV2, which is again a random variable, but now you see its variance is very high. It's fluctuating very wildly in comparison to the blue one. But the linear relationship is not evident from what we have done so far. So what I'll do is that I will make a scatter plot between these two variables and see whether they are having linear relationship or not. So I'll just enable my settings in the plot, and I'm just going to generate a scatter plot, and here we are. So my x-axis is my random variable 1, my y-axis is my random variable 2, and since we had created a linear relationship between them, we can see that they are correlated. As random variable 1 increases, random variable 2 also increases along with it. This is what this relationship is capturing through this slope, and this slope has primarily come because I have used this number 2 to multiply it by random variable 1. So clearly we have been able to generate a synthetic data set having two random variables, two sample points, which are linearly correlated with each other, positively correlated. Now, just for a second, I am going to expose you to two equations, and I will not explain where these equations have come from, but I want to show you what happens if I multiply random variable 1 with this coefficient, and towards the end of the presentation I'll explain where these numbers have come from, and random variable 2 with this number, this coefficient, to generate another variable called xx, and then I'm going to generate a variable yy by multiplying random variable 1 with this coefficient, essentially the same one which is up here, and then random variable 2 with this coefficient, which is the negative version of what's here. And I'm going to again do a scatter plot between xx and yy, and something really interesting happens when I do that. So this is the scatter plot between xx and yy, and this is the scatter plot between random variable 1 and random variable 2, and let's see what happens. So my blue data is my original data, and my orange data is coming from xx and yy variable, and you'll see that something very interesting has happened. So this was my original data, and if I, now what has happened is, take this as pivot point and rotate this data in this direction. So this entire data set has flipped, and it's lying now on x-axis. So you see these 2 points, they have come here, and you see this outlier point here, it has gone here. So by doing this, I can rotate the entire data set, and it has got a lot of statistical repercussions. The first one being, if you see in my original data set, that is this blue dots, if I move in the direction of increase of random variable 1, I also get increase in random variable 2, which is exactly what linear correlation is all about. But once I've rotated this entire data set, when I move in this direction where RV1 or whether PC1 is increasing, and I'll explain what PC1 is, nothing much happens on the y-axis. And similarly, when I move in this direction, nothing much happens in this direction to the data set. I'm talking about these orange points now. So essentially, we've been able to remove the correlation in the data set, and this is one of the key factors of principal component analysis. And how it's going to be used will be demonstrated subsequently. But most important part is that this equation has come from somewhere, and we need to find out where it has come from. Moving forward, I am going to now do the principal component analysis, for which I'm going to stack up my two random variables together in a data set, and then I'm going to create a data frame out of it, and then I'm going to do principal component analysis on it. So this piece of code says that I am doing principal component analysis, which is essentially nothing but if you see here, it is a singular value decomposition, which is very similar to eigen decomposition. Remember, eigen decomposition is for square matrices only, but singular value decomposition can be used for non-square matrices as well. Here we have a case where a non-square matrix is there, so we can use SVD instead of eigenvalue decomposition. So I'm saying is that I'm going to take two components, that is principal component 1 and principal component 2. And once I have instantiated this object, I'm going to pass on my data. My data is here, which was comprising of these two random variables. And then once I have transformed the data, essentially this piece of code is just rotating the data as I mentioned earlier. And then I'm going to calculate the covariances of both the original data. This is the covariance of the original data, and this is the covariance of the rotated data. This is what is the PCA transformed data, and see what happens to the correlations. So rest of the code is essentially there to create correlation matrices and their visualization. So here we are. So the matrix on the left is coming from the original data, and here on the y-axis we have random variable 1, random variable 2. On the x-axis again we have random variable 1, random variable 2. These are the on-diagonal elements and these are the off-diagonal elements of the covariance matrix. So this is the variance of random variable 1 and this is the variance of random variable 2. And as you can see that the variance of random variable 1 is lower than random variable 2. And that's quite evident from this graph. As you can see, we are not talking about these blue points. And if you see this, when we talk about random variable 1, which is on the x-axis, the values of data are fluctuating from -5 to just about +4. So the fluctuation in this direction is limited between -5 to 4. However, when we go to this direction, you can see that the lowest point is at -10 and the highest point is at somewhere around +10. So variation in this direction is much larger, which is why the random variable 2 is having a higher variance in comparison to random variable 1, and which is exactly what is captured by this covariance matrix plot. The bluish colors are close to 0 and the yellowish colors are close to 16. And you can see that firstly, this has lower variance, random variable 1, and the random variable 2 has higher variance. Second part is these off-diagonal elements. So these off-diagonal elements show, firstly, both of them are positive. That means they are showing a positive correlation, and they are a very large number, which is what is signifying a positive correlation between random variable 1 and random variable 2. And which is what was explained earlier. As random variable 1 increases, random variable 2 also increases along with it. In fact, much sharply. So this is the original covariance matrix, and then we did something. We transformed this data here and then we calculated the covariance matrix and we plotted it here. So this is the plot of the transformed data, and something really interesting is happening here. So this is principal component 1, principal component 2, and here principal component 1 and principal component 2. These are the diagonal elements of the covariance matrix, which are basically variances. And what it's saying is that the variance of principal component 1 is much higher than the variance captured by principal component number 2. So, and which is also very evident. If you see, now we are talking about this orange data point. The data has been transformed to different axes, and now principal component 1 is lying along the x-axis and principal component 2 is lying along y-axis. And as you can see, variance in this direction, the fluctuation is in this direction is much higher than variance in this direction. And that's the reason variance of PC1 is much higher in comparison to variance of PC2, which is just about this much fluctuation, I think between plus and -1. And that's exactly what is captured by these two numbers. Most important point are these off-diagonal elements. So as I told earlier, that these are variances and these are covariances. So here also these are covariances, and these covariances have gone to 0. And when covariance goes to 0, it means the correlation between the variables has got eliminated. And this is exactly what has happened here. By doing this rotation, if I move in this direction, just consider these orange points. If I move in this direction, there is no clear-cut pattern that emerges on the y-axis. And similarly, if I move up and down in y-axis, there's no clear-cut pattern of data that appears on the x-axis, suggesting that the correlation between these two components is now 0. And we do this transformation for a very special purpose, which will become evident through this piece of code. So basically, what this transformation has done, or the single value decomposition has done, is that it has allowed PC1 to capture the largest possible variation in the data set, and a small component of it has been captured by PC2. How much it is, we'll just have a look. So these are called variances explained by the principal components. And this line of code is basically finding out what percentage of variance has been explained by PC1 and what percentage of variance in the data set has been explained by PC2. And as you can see, principal component 1 has been able to capture 99% of variance in this data set, which means it's a very dominating factor. PC1 is the dominating factor in this analysis, and PC2 has captured only 1% of the variation, which is very evident because if you see this orange data set, most of the variation is happening in this axis, and that axis belongs to PC1. Now, we would also like to understand where these, where these coefficients came from. And essentially speaking, they are nothing but they are the eigenvectors of this particular data set. And this is how we are going to calculate them. So let me just run the code one more time. And what I'm doing here is that I'm trying to find out what is the linear combination of random variable 1 and 2, which is resulting in principal component 1 and principal component 2. So essentially, this is one eigenvector of this data set, and this is the another one. This has come from the transformed data set after decomposition. So PC1 essentially is a linear combination of random variable 1 and random variable 2, and these random variables have a coefficients which are directly coming from the eigenvector. So actually, if you see this, random variable 1 is getting multiplied by this number has come from here, and random variable 2 is getting multiplied by this number, which is coming from the eigenvector. And these and similarly for principal component 2, this is the eigenvector. So random variable 1 is getting multiplied by this coefficient here, and random variable 2 is getting multiplied by this coefficient. And these are exactly the same equations that I have earlier captured here. And now you understand where I have got these coefficients from. Essentially, they are eigenvectors of this data set once we have transformed it. So now the analysis here is, firstly, we have understood that principal component 1 is the most dominant in comparison to principal component 2, because this explains this captures 99% of the variation in the data set, and this one just captures 1. So for all practical purposes, we can ignore this. And in this PC1, what is the most dominating factor? So that is analyzed from here. As you can see, the coefficient attached to random variable 2 is 0.89 or almost 0.9. And on the other side, the coefficient attached to random variable 1 is almost half of it, which means this coefficient is bigger than this coefficient, which means random variable 2 is causing maximum amount of variation, and that's why PC1 is able to capture maximum amount of variation. And second part is that both these coefficients have same sign, negative and negative, which means they move in the same direction, which means they have positive correlation. When they move together in the same direction, and this is why they have the same sign. And random variable 2 is the most dominating one in principal component 1, and principal component 1 itself is most dominating in comparison to principal component 2. And in principal component 2, we see that the larger coefficient is multiplied by random variable 1, but since PC2 is explaining only 1% of the variation in the data set, this does not even carry much meaning. Now, the takeaway from this is that if, for example, if this was stock data, random variable 2 was one stock and random variable 1 was another stock, by doing this principal component analysis, we would have immediately come to know what is the most risky asset, what is the most volatile asset, and how it is contributing to the overall portfolio in terms of returns as well as risks. Now, this concept will be amplified in the next case study.